Where we left off last time was talking a bit about Java 7 features, the so-called object-oriented features in Java. What we're going to do now is talk about the functional programming features which began in Java 8. And so I'll talk about what the concepts are underlying functional programming, and then we'll give an overview of the features that Java now supports. These features were initially added in 2014 with Java 8, and then they've been expanded to some extent since then. I believe the latest version of Java is Java 12. Most of what we're going to cover here was in Java 8. There'll be a few things here and there I'll point out explicitly as we talk about completable futures, as we talk about parallel streams that had additional features added later in later versions of Java. Sadly, we cannot take advantage of those features in Android because they only support Java 8 at this point. Another thing we're going to do in this discussion is we're also going to compare and contrast the functional programming features we're going to talk about now with the object-oriented programming features that have been in Java since its inception. And you'll hopefully come away with an idea of why you would choose which set of features under which circumstances. And they actually work together very nicely. So functional programming has its roots in something called lambda calculus. So you can read about functional programming here at this Wikipedia link. And basically what lambda calculus does, it's a formalism that treats computations as the evaluations of mathematical functions. And in pure unadulterated functional programming, you only have things called pure functions. And what a pure function means is that the function only gets its input from parameters that are passed to it and does some computation and only returns the results as its output, either a return value or through some other means. But there are no side effects, and we'll talk about that later. One of the key things you'll see very popular in functional programming is the concept of function composition, where the output of one function serves as the input into the next function. And this will become very, very clear when we talk later about Java 8 streams, where you can actually pipeline a bunch of functions together in a chain, if you will, and you can transform the input and the output in very clean ways. And then you can also parallelize them, as we'll see later. Here's a very simple example of computing the nth factorial using Java parallel streams. And in fact, you can go to the ex16 folder in my GitHub repository and see this code plus a bunch of other stuff to illustrate the point. So here we have a method factorial that takes a long n, so you want to compute the nth factorial. And what it does is it creates a stream of values from 1 to n inclusive, so it's including n. And for each value in that range, in parallel, it will go ahead and multiply each pair of adjacent values together, and then it'll keep doing that until it creates a single reduced result, which is the nth factorial. And we'll talk about this later when we get into parallel streams as to whether this is a win or not. You'll see that for longs that are the primitive type long, it's actually not a big win to run it in parallel. When you start replacing primitive longs with arbitrary precision arithmetic, like big integer, and you get n being very large, then parallel processing makes a lot of sense. But the key point here is just this idea of having a stream of values that you do something to, and it's all nicely composed together where the output of this range closed function serves as the input to the reduce function. And we'll talk more about this later. One of the key things with functional programming is the idea of trying to either eliminate altogether or, at the very least, minimize the use of side effects and changing state. So the whole concept of mutable shared data, especially mutable shared data that's shared between multiple threads that could be running on multiple cores, that's considered to be very problematic. And you'll see as we get a little further into this later in the course why it's problematic. And it's problematic because it makes it difficult to reason about your code, and it also makes it difficult to optimize the code, and it makes it difficult to parallelize the code without having all kinds of bad race conditions and other hazards of concurrent programming. Here's a very simple example to illustrate this. This is a different implementation of factorial that's buggy, so it's buggy factorial. And you'll see in a second why it's buggy. What we're going to do here is inside the factorial method, we're going to create a new local variable t of type total, and here is total. You can see that total is a class that has a long, which we initially set to 1, and it's got a method called mult, for multiply, where you give it n, and it multiplies the total, the m total field by n. Well, that looks sort of innocent enough, right? But this is what's called shared mutable state. Well, it's clearly mutable because we're changing m total to multiply it by itself and n. So that's mutable. But why is it shared? So if you take a look here, you can see that when we say long stream.range close 1 to n, that causes all the code for the computations done here to run in parallel in different threads. And on most modern multi-core processors, or most modern processors which are multi-core processors, you'll end up with each of these threads being mapped to a separate core. So they will all physically run in parallel. And as they're running in parallel, you can see that for each of these threads running on the different cores, we're going to go ahead and multiply the value of m total by n. And the problem here is that m total is shared because there's only one instance of it, and yet all these different threads are multiplying this thing at the same time, and there's no protection for those values. So this will lead to something called race conditions. And race conditions occur when the proper functioning of a program depends on the order or the timing of the operations. And race conditions, as you'll see, are kind of the root of all evil, and well, maybe a better way to put it, shared mutable data, shared mutable state, is the root of all evil, and that is because it induces or causes race conditions. And there's other problems here as well, having to do with returning m total here in a way that will cause problems with memory visibility. Won't talk too much about that. If you're curious about it, you can read this article talking about atomicity, visibility, and ordering in Java, and why you have to be very careful how you do this stuff. But the bottom line is that this code is absolutely full of bugs. And a good programmer would never write code like this. A good programmer instead would write code like this. This is the same computation as we saw there, except this code does not incur race conditions and will parallelize very nicely, modulo the fact that you should use a big integer, not a long, if you want to actually get a speed up. But be that as it may, there's no race conditions. So race conditions are a big problem. We'll talk later about how Java 8 provides a whole bunch of cool features to make the need for locking and synchronization kind of disappear, which would be the other way you would handle this. Another way to solve this problem historically would have been to make mult a synchronized method, but that has its own set of headaches with respect to overhead. So anyway, the key point is that changing state can be problematic because it makes it difficult to transparently parallelize your code. The other thing to remember here is that only you can prevent these concurrency hazards. The compiler will not save you. The Java virtual machine will not save you. You are responsible for knowing how to write the code, either by using proper Java 8 features like parallel streams or completable futures, or by using more traditional Java synchronization mechanisms like reentrant locks, synchronized methods, synchronized statements, and so on and so forth. There's a whole pile of those things. If you're interested in more of the synchronization side of the world, then the class I teach next semester in the spring will go through synchronization in great detail. We don't cover synchronization much at all in this class, and the reason for that is that these Java 8 features we're going to talk about really alleviate or eliminate the need for synchronization in most cases. So if functional programming isn't about changing state and mutable shared data, what the heck is it about? Well, what's it about is so-called immutable objects. And these are objects whose state cannot change after they are constructed. Which, when you first think about this, you say, wow, that's a pretty stringent limitation, isn't it? Well, ironically, there's a very popular class in Java that you've undoubtedly used before if you've programmed with Java very much, and that is Java string. And Java string is an immutable object. So you can learn more about Java string here, and I'll show you why it's immutable. It's immutable because if you look carefully at string, its data members are all final, which means that once they're set in the constructor, they can't change. And all of its methods are simply accessor methods. So there are no mutator methods on string. There's nothing you can call on a string that will change the state of the existing string. All you can do is make new strings. So there's methods like substir, for example, which will make a copy of a subsection of a string and make a new string. And once that's created, it's immutable. So it turns out that immutable objects are actually very common, even though at first glance they seem a little bit odd. Another property, another key concept of functional programming is the idea that behavior can be parameterized. Now, we're all very accustomed to parameterizing data. So if you go back, just as an example, if you go back and you take a look at the constructor for string. So strings constructor takes a string, right? So you can create a string from another string. So it's pretty clear that you can parameterize data. You've been doing that since CS 101 or whatever your intro programming course was before that point. But parameterizing behaviors, that's a little bit different. And so let's just take a very simple example here. We'll see lots and lots of examples as we go through the class. So here's an example of parameterizing behavior. So we're going to make ourselves a list of threads. And we do that by saying arrays. Arrays is a helper class. It's called a utility class. We say arrays.asList, and then we give a list of threads. And it's going to turn that into a list. So it's going to take an array of something and make it into a list. And as you can see, we're going to have threads be new thread Larry, new thread Curly, new thread Mo. So that's the Three Stooges. For various reasons, you'll see Three Stooges show up a lot with my examples. If you've never, this may be somewhat of a cultural thing. If you've never seen the Three Stooges, this won't be the least bit interesting. But if you've seen the Three Stooges, they're some rather slapstick vaudeville-style characters from, I think, the maybe 40s and 50s that were always doing physical comedy, hitting each other over the head and stuff like that. So we make ourselves a list of stooges, and then we're going to go ahead and sort that list. As you can see, the list initially is not sorted. So we have Larry, Curly, and Mo, but we want to have Curly, Larry, and Mo, because that would be the sorting of that. And the way we're going to do that is we're going to call the sort method on the threads list, and we're going to pass in a behavior, which is something called a method reference, which we'll talk about in a second. And this method reference basically says, sort this list by the name. And the way we know it's the name is it's thread : get name. So that says, sort this list using the get name method, or this get name behavior, in order to figure out how to order these threads. Okay, so we'll cover this in more detail. I'll talk about what a method reference is. We'll break down what it means to do sorting with a comparator, comparing in more detail later as well. Some really cool stuff there. So now that you've had a very, very introductory taste to functional programming with those key concepts, right? Computations are treated as the evaluation of mathematical functions, avoid changing state, avoid mutable shared data, focus on immutable objects, and you can parameterize behaviors. Those are the sort of the 3 or 4 key themes of functional programming. Let's kind of compare and contrast functional and object-oriented programming. So object-oriented programming, which hopefully you all know about, and as I think I mentioned before, we're going to have a short quiz this Wednesday, the day after tomorrow, just making sure you understand the basics of Java object-oriented programming. Object-oriented programming is really about hierarchical data abstraction. So what the heck does that mean? Well, you can see an example here. Here we have an interface like Java iterator. So that's data abstraction, right? We just have an interface. We don't expose the implementation details. And you can derive or inherit or implement, depending on your choice of terms, different classes that will create a hierarchy of classes that will implement iterators with different traversal orders in this particular case, right? So we might have a pre-order iterator, a post-order iterator, an in-order iterator, a level order iterator. If you've taken the CS251 class with Graham Hemingway, you probably are familiar with the way he had the expression tree examples. This is kind of based on that. So you have some kind of interface, and then you have different implementations which are going to form a hierarchy. In an object-oriented program, components that are the units of design and units of composition are based on class roles and relationships that are stable. In other words, once you define the classes, you do some domain analysis, think about what methods you need, think about how cohesive they are, how loosely coupled they are relative to other classes or interfaces, and you kind of think about the structure, the cookie cutter pieces that we talked about before. And then you make your solutions extensible by using features like inheritance and dynamic binding. So as you can see here, we have a component node, which can then be derived to make a leaf node or a composite unary node, composite binary node. Then we can have different kinds of composite binary nodes, different kinds of composite negate nodes, or unary nodes rather. And you can have a whole hierarchy of these things. And if you take a look at the implementation, you'll see that we're overriding various methods like except, like left child, right child, item, and so on and so forth. And you can use the hierarchy to be able to customize or specialize the method behaviors as you move down the tree. And then at runtime, the compiler will set things up to pick the right method based on the type of the child with an interface it derives from the parent. And this is intentionally done this way. We do things based on stable class roles and relationships instead of basing our design around functions that correspond to algorithmic actions. And most of you, probably for better, not worse, but most of you probably don't even remember what it was like to do algorithmic decomposition. That was the early way that people designed software back in the bad old days, back in the 60s and 70s and early parts of the 80s. We don't teach that anymore, thank goodness. But that was about stepwise refinement with basically algorithmic decomposition. You'd break things up into chunks that were functional or actions. In an object-oriented program, state exists and state is mutable, but state is encapsulated by methods that perform imperative statements. In other words, they do things that change the state of the program. But you hide the representational details. If you think back to the types of things we talk about in CS 101, undoubtedly you've learned about how you could have the concept of a stack, and then you could have a stack implemented as an array, you could have a stack implemented as a linked list. The details of how the stack was implemented, whether it be a linked list or an array, are not exposed through the interface or the API that programmers use when they write their applications. So that's what object-oriented design is all about. And but they're imperative. So here's a simple example. We have a little iterator that we talked about before. We're going to iterate through every element in our expression tree. And as you can see, we're going to use has, next, and next, which are basically methods that say, is there still anything we haven't looked at yet in the tree, in the collection? If the answer is yes, then we get the next item and do something with it. But that requires updating state, right? Under the hood, we're changing the state of the iterator. In fact, you'll see when you do assignment 1A, if you're a grad student, or assignment 1B, if you're an undergrad, you'll end up implementing these various iterator-like mechanisms. And you'll see that state is being changed. So what that says is that in object-oriented programs, state is often mutable, though typically encapsulated. You don't see it, but it's being changed behind the scenes. OK, so that's basically a quick overview of functional concepts and then kind of comparing and contrasting object-oriented and functional paradigms.